Okay, so we can start with our first presentation for today. So our first speaker is Zhongzhi Yu. He's a second-year Ph.D. candidate at Rice University, and he will be presenting his work on LDP, Learnable Dynamic Precision for Efficient Deep Neural Network Training and Inference.
Hello everyone, my name is Zhongzhi Yu from EIC Lab at Rice University. Today I'm going to present our paper called LDP, Learnable Dynamic Precision for Efficient Deep Neural Network Training and Inference. So as you may all know, deep neural networks has been really powerful in recent days. Specifically, it can achieve a surpassing human level performance. For example, on the widely used image classification task, on a large-scale ImageNet dataset, the recently proposed DIT-based model can surpass the human performance by over 1% of accuracy. And a similar pattern has been observed on neural language processing tasks, where the recently proposed Albert model can also surpass the human level performance by 2 points on the commonly used GLEU benchmark dataset. So it still worth to note that coming along with a powerful deep neural network performance, there also comes with a challenge that deep neural networks are pretty costly, both in terms of training and inference cost. For example, in training, the aforementioned DIT-based model on ImageNet will take over 53 hours to train with a node of 8 V100 GPUs. And also for inference, to do inference on a single image, the DIT-based model will has a latency of 137 milliseconds on a commonly used edge device, NVIDIA TX2 edge GPU. This means that we can have a summary of the secret formula of a high-performance deep neural network is the powerful computers along with large deep neural networks. However, such a combination comes with a unique question is that large deep neural networks with prohibitive training and inference cost cannot align with the recently growing demand for on-device training and inference. Specifically, because on-device scenario has limited computation, so that we cannot either deploy the deep neural network or even to run it on the edge GPUs. And to alleviate such gap, low precision method has been proposed as a promising direction, because in low precision method, people trying to trim down the redundancy of deep neural network from the most fine-grained and redundant deep bit dimension. In existing low precision method, static low precision training has been proposed for a long time and been like a commonly used scenario where people use the same precision during training. However, this is a really straightforward drawback of the static low precision training is that it will suffer from significant accuracy drop under low precision training scenario. One of the promising directions to elevate the accuracy drop of static low precision training is to introduce the dynamic low precision training, where people assign different precision for different training stages as shown here. However, there are also two non-neglectable drawbacks of existing dynamic low precision method, that they only consider the temporal dynamic precision, meaning how to allocate different precision for different training stages. And also it needs non-neglectable manual efforts in hyperparameter tuning, because they need some extra hyperparameter to decide how to generate the temporal dynamic precision schedule. This will limit its wider adoption when we want to apply it onto new tasks or new model and data sets. So two natural questions coming along with the existing situation of the low precision method is that, first, can we automate the generation of dynamic precision allocation during training? And the second is that should we also consider the spatial dynamic precision in addition to temporal dynamic precision? We will first have a really brief exploration about about our second question here, where from existing works we find that in the deep neural network, different layers have different sensitivity during training and have different sensitivity towards different input sample. And also, a recent work showed that precision has a similar effect as a learning rate. So that we argue the spatial dynamic precision allocation is also a non-neglectable component to achieve a better dynamic precision training. So we do the following experiment to show the importance of spatial precision allocation. Specifically, we generate a training schedule that consists of the temporal and the spatial precision allocation, as shown in this table here. We divide the ResNet 38 training on CIFAR 100 dataset into 4 stages, and for each stage, we allocate different bit widths to first 3 blocks into a ResNet 38. Let's take this setting for example. This means that for 0th epoch to 30th epoch, we assign 4 bit for the first block, 6 bit for second, and 8 bit for third. And here's our overall training setting. And we observe that both temporal and spatial precision allocation matters toward the achievable accuracy after dynamic training. Specifically, different combination can lead to as high as 0.75 accuracy gap, showing that it is really important to also consider how to allocate precision both in spatial and temporal dimension. However, this comes with a new question, is that because the temporal and spatial precision allocation strategy could be extremely complex, and how can we automatically generate the spatial and temporal precision allocation during training without introduce any extra training cost? To this end, we propose our LDP framework. Our contribution can be summarized into following 3 bullet points. Is that first, we propose the Learnable Dynamic Precision, LDP, a framework to automatically learn the spatial and temporal precision allocation during training. The second is we develop a differentiable method to enable the end-to-end learnable dynamic precision deep neural network training. And the third is our LDP achieves state-of-the-art accuracy efficiency trade-off on 7 deep neural networks, 5 datasets, and 3 tasks in both training and inference. So we'll first introduce about our LDP framework. Let's first take a brief review on the vanilla training pipeline, where the input is passed through the weight and activation of each layer to calculate the final task loss, and then do backpropagation to calculate gradient and update the weight parameter accordingly. To achieve the layer-wise learnable precision, we did the following modification on top of the vanilla training pipeline, where we add a layer-wise learnable precision to each layer in the network, and we add an additional cost loss into on top of the existing task loss to penalize the layers with excessively high precision value. So that with such a designed pipeline, we can automatically learn the spatial, as shown here, and temporal, as shown like here, precision allocation during training. However, to achieve an effective framework, only pipeline is not enough. There are 2 enablers of LDP. The first is differentiable learnable precision, and the second is loss function design. And the following, we will introduce these 2 key enablers that making us be able to develop a differentiable method with end-to-end training. So first, the differentiable learnable precision. One of the really straightforward challenge about achieving learnable precision is that how can we achieve a differentiable update toward precision on top of the discrete precision value? We can first take a review at the vanilla quantization process, where the quantization output is calculated by input, the 0 point on input, and quantization step. And here, quantization step is defined as the dynamic range of the input value and also the precision value here. So we find that it's possible that we can use the quantization step as a bridge to map to map the quantization output with our precision value to achieve a differentiable update toward precision value itself. And to enable this, we introduce a layer-wise learnable parameter beta and modify the quantization step function from here to this formulation. Namely, we change how we calculate this interval here. The second enabler is the loss function design. Because we want to make our LDP to be a general framework that can be applied on top of a wide range of application, datasets, and models without the need for extensive hyperparameter fine-tuning. So that how can we balance the accuracy and efficiency trade-off when the scales of task loss and aforementioned cost loss varies across different tasks and during training? We achieve this, we solve this challenge by a two-step. The first is we only penalize the training cost when it exceeds user-defined threshold T. And also, we balance each layer's precision gradient with respect to task loss and cost loss, as shown as described in this function below, where we can find like the precision gradient is actually calculated by original gradient to the task loss and a cost gradient of cost loss multiplied by a scaling value, which is calculated by the running mean of absolute value of the task loss and gradient loss and cost loss gradient. Finally, we evaluate our LDP framework on 7 models, 5 datasets, and 3 tasks over 3 baselines, including the static low precision baseline, which is SBM, and 2 dynamic low precision training methods called PFQ and CPT. We first observe that our LDP can generate effective dynamic precision allocations. Specifically, the automatically generated precision of LDP can even outperforming the human expert designed allocation by 50.1 reduction in inference cost, 25.2 reduction in training cost, and 0.28 improvement in terms of accuracy. It's worth to note that our LDP is the first dynamic precision training method that can automatically benefit from the inference cost, because after training, not all precisions are necessarily stopped at the highest precision. So this can be we can achieve a training accuracy, training cost, and inference cost triple win. To validate whether our LDP can be easily transferred to other tasks, we also use the language modeling task, which is a common task in neural language processing, to evaluate our LDP framework, where we observe LDP achieves 0.96 reduction in terms of perplexity and 25.9 reduction in terms of training cost without any need for hyperparameter fine-tuning. For more results on more datasets, tasks, and models, please refer to our paper. And finally, we want to see whether the learned precision of the LDP framework makes sense. So we first visualize the block-wise average precision of ResNet38 trained on CIFAR 100 datasets, as shown in this figure here. Each block represents a block in the ResNet38 model, and the size of this block represents the spatial resolution of the input feature map. And also the color of this block indicates the value of the learned precision, so that the darker the color is, the higher the precision are. We observe that our learned precision is consistent with existing observations. Specifically, we find higher precision in the blocks after downsampling, and also higher precision in the deep blocks with the lowest spatial resolution. This is consistent with some recent works where it also visualized the redundancy of ResNet, showing that by automatically learning a precision, our LDP can find the redundancy in a deep neural network, which is and has a similar observation as human-designed techniques. And finally, we try to see what more insight can we draw from our learned precision allocation. We visualize the layer-wise average precision of the DIT tiny model trained on ImageNet, as shown here. Similar as the previous figure, each block represents a layer in the DIT tiny block, and the color of each block indicates the precision value. The darker, the higher. We find that our learned precision can even potentially guide the future model design. That's because we find there are lower precision in the first fully connected layer and also gradually decreased precision in the last 3 fully connected layers, showing that in vision transformer, a stack of fully connected layers may not be effectively trained and has a large redundancy. This is consistent with some recent research direction where people try to see how can we better modify the fully connected layer in vision transformer to achieve a better accuracy of the vision transformer. And here is my presentation of LDP, Learnable Dynamic Precision for Efficient Deep Neural Network Training and Inference. Thank you for your time. Do you have any questions?
Hi, I'm Tony from Resilience. It was really interesting. Forgive me if I don't quite understand it, but I'm just trying to wrap my head around the beta is going to be a float. So in your final precision, are you just rounding to the nearest bit? When you actually, you see what I'm saying? Like you're doing a fraction of a bit. Yeah. So do you just round up to the nearest bit?
Yes, we do a round up.
Thank you.
Yeah, thank you.
Kamilkar from Analog Devices. Thanks for the presentation. My question is about accuracy increase, actually. So you have showed that not only your model size decreases, but you can also increase accuracy by doing this kind of learnable dynamic precision. So are you widening up your model just because you have decreased the quantization? So are you scaling up your model size? How can you achieve accuracy increase?
So do you mean, so just to confirm, are you asking whether we scale up our model size during training to achieve a higher accuracy?
I mean, yes. For example, instead of 8 bits, using 8 bits at inference, if you use 4 bits, then are you just increasing number of parameters in a layer? Or this was my question. Maybe I could not understand that point well.
Yeah, thank you for your question. We did not scale up the model. So our setting is as follows. We set a precision range, for example, like 3-bit to 8-bit during training. And for baseline model, for example, like the static low precision training, we use the 8-bit model, which is the highest achievable redundancy or highest achievable model size of our LDP framework, so that we can safely say that the results of our LDP framework is achieved with a model with a smaller model complexity compared with our baseline model.
Okay, I see. Thanks.
Thank you.
Yeah, thanks for the presentation. It's interesting. I'm Ashutosh from Infineon. The question I have is, how did you measure improvement in training efficiency? And the sort of the background for my question is that, given that you have kind of increased the complexity of the training, right? And also you are deviating from the sort of the architecture of the underlying hardware, right, which is designed for 816 bit boundaries, right? Now you're handling kind of odd boundaries. So I can imagine there is going to be, additional overhead in sort of handling all these use cases. So how did you see that? What was your method to figure out that you got 25% improvement in efficiency? Was it like a paper exercise or you measured it somewhere?
We measure training efficiency improvement in terms of the flops. So are you asking about this metric or?
Yeah, because the thing is, like, if you do a theoretical sort of analysis, that may not translate into practice, because now you're actually the training efficiency, your training methodology is a lot more complex. You are doing more gradients and you have additional cost function. And also your data movement is not going to be seamless, right? Because you don't have 5-bit machine under the hood.
Yes, so, okay. I think from here, let me clarify the training process of our LDP framework. If you can recall this function here, we can actually, because the network architecture is fixed, right, during training, so that we can pre-compute the gradient of the cost loss before we train the network. That's just a one-time effort. And after that, we can just directly use the pre-calculated loss gradient, a cost loss gradient, and apply it on top, combined with the in-time calculated task loss gradient. so that our method actually do not lead to additional cost in each forward and backward iteration during training. And the actual training computational cost is the same as normal training. Yeah, that's the first one. And for that's the first one about the training cost for each iteration. For the second part about data movement, because we are working on we evaluate the LDP as a preliminary evaluation on whether such a learnable precision method can work, and also can it lead us with some additional insights, so that we mainly calculate with the flops, and we did not run it on the real device settings. So, but that will be a future work of our LDP to build a accelerator or something to more fit our mixed precision update pipeline. And based on my knowledge, I think that's doable, because there are like many recently proposed mixed precision accelerator where they also focus on a similar scenario with mixed precision during training and inference.
Okay, thanks. Quick question. So your quantization is just
sorry.
the weights, not activation?
Since we are running out of time, is it possible we can take it offline? Thank you very
we can
much.
discuss offline maybe.
Thank you.
Thank you, Zhongzhi.
Yeah.
It's great that we have an engaging.
Yeah, thank you.
It's great we have engaging discussion here. So.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Gravity, Hymex, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.